All right, everyone. Welcome to the 2019 Diego project update. I'm Sunjay Bhatia, engineer on the Diego team.
And I am Amin Jamali, one of the Diego engineers on the team. Today, we're going to talk to you about some metrics that measure success for us and our users. We'll focus on speed, stability, scalability, savings, and security, and how it relates to the work we've done over the past year and continue to do over the next few months. For each of the 5 S's we have here, we'll go into what each one of them means for our team, and some have to do with the components that we work on a day-to-day basis, and the other ones have to do with some of the processes that we have.
All right, so speed first. We expect to move quickly and deliver features to our users and reduce feedback loops. That's what we think of it as part of the Diego team. We want to execute on our backlog quickly, so we're continuously providing value to our users, and so then they can in turn move quickly. So what have we been doing to execute on this? We've been kind of consciously trying to flatten our team out and distribute responsibilities across team members. We've also kind of intentionally for a while been trying to keep ourselves to a consistent release cadence to get feedback faster and give users what they need. And recently we started trying to make Diego a little bit more maintainable for our team. So we're working so that individual team members can work quickly and we can potentially onboard new team members faster. And as the Diego team, we're a pretty central component in the Cloud Foundry runtime. We're required for a lot of other teams to get the features that they want through to their users. And so as an integration point, we've tried to highly prioritize these cross-cutting features and collaborations with other teams. So some examples are OCI mode, with collaboration with the Garden team, in order to increase the speed at which you can scale your applications and create containers. Instead of having your application droplet be a tar file that's copied into a container, it's now actually, there's a feature where you can actually make that a container image layer. We've also tried to work with the Garden team to calculate more accurate CPU metrics, with the Garden Windows team on route integrity for Windows, so that TLS from the Go router to your applications is, communication from the Go router to your applications is over TLS. Bring that feature as a beta experimental feature for users on Windows. And also more parity with Windows and CFSSH with NSXT and other external network plugins, so you have the same experience across Linux and Windows. We've also worked with the build packs and CAPI teams on bringing sidecar support to the platform, and with the CAPI team and the observability teams on tagging logs and metrics for your applications with more information, so you can, as a downstream consumer, you can aggregate these things more effectively and don't have to do as much work putting all that information together yourself.
Next up, we have stability and scalability. As the team, as our team, we expect Diego components to keep running and to keep your apps running. We've come to expect of Diego to perform well in large installations running thousands of apps, and we should continue to expect that from Diego and improve and refine and improve on this experience. To be a bit more specific, issues that happen at scale can be attributed to some of the environmental faults, which the system should continue to be more resilient to. We worked on various features over the past year that help solidify and improve on the Diego components as far as the stability and operation at scale goes. To name a few things, we'll start with NATs. NATs failures are common in installations where messages are somehow missed. Specifically, this was an issue where deleted apps remain routable in some scenarios. So we've lowered the chance of running into this issue by having a cache of that removals. Another issue we've had previously is the network failures. As you know, build pack, sometimes there's network failures in the system. So we've improved on that with the task retries that we have built into the Diego now. If you have seen app start failures due to not having enough disk space before, We've improved on that, worked with Garden team to have a new property that actually shows you a proper error message, and it actually fails faster during the staging time with not having enough capacity. The last one, but not the least, is the improving the SQL connections for Locket. This has been an issue in some of the larger installations where Locket has held on to some of the SQL connections, and we've improved on that as far as the connection lifetime goes, and actually without actually impacting the performance. There's new metrics there in order to figure out in order to help monitor that usage over time.
All right, now let's take a deeper look into one of the problems that we addressed in the past year. Before we start, just for anyone who's unfamiliar, we're going to be talking about Locket, which is Diego's distributed locking component, which is backed by a SQL database. The BBS and Auctioneer use it to maintain which of the many nodes is the active one. And also the Diego cells periodically check in with Locket so that the Locket can keep track of which cells are available for the control plane. The BBS ends up using this information from Locket to make some decisions during convergence, which is the process of converging the desired state from the cloud controller and the actual state of the world that's running in your foundation. And when the BBS makes decisions about changing the state of an LRP, or if an LRP crashes or whatnot, it sends events to the route emitters that run on each cell. They communicate with the Go router about existing routes, and they get this information from the BBS via events. So here we have kind of a diagram about what expected kind of steady state of a system would look like. We have a BBS that has 3 LRPs. 2 are running on cell 1, 1 on cell 2, and Locket has a record of each of these cells. They're both checking in with Locket periodically. However, in real environments running at scale, there's environmental faults that happen, the network latency, et cetera. What happens when a cell is unable to check in with Locket for some amount of time? The cells are periodically checking in with Locket to make sure that the state of the system is updated. So what happens to the work running on a cell that is unable to check in with the control plane? So in the past, before the changes that we made recently, when the cell 1 was unable to talk to Locket, the BBS, it notices this during convergence, which runs periodically, and the LRPs running on that cell are replaced. The BBS tries to replace all the LRPs on this kind of missing cell. And what actually ends up happening is you get downtime in your application because those new replacement instances shadow those old instances. So why does this shadowing happen? Fundamentally, we always represented LRPs as groups. In the API, in all our internal logic, we had endpoints, and all of the endpoints to fetch LRPs and all the event endpoints grouped LRPs together. A group is basically the potentially evacuating instance and the kind of ordinary regular instance that correspond to an individual application instance. This was easy for representing evacuation and routing and made our lives easier in that regard, but it actually has a missing bit of nuance here. There's actually potentially, because of the missing cell problem, kind of a third LRP that could arise, a third type of LRP, which is kind of we're calling it a suspect LRP. So in the case that we described before, when a cell goes missing, the LRPs on that cell, we don't really know what's going on with them. We don't know what's happening with that cell, technically. So when we immediately try to replace them, the replacements shadow the routing information for that cell. The route emitter is told, basically, that the new instances should take over, and the Go router is told that there's no more routes for that instance. So you get a short period of time when the replacements are starting up where you get 502s potentially to your application. So what did we do to fix it? Instead of grouping LRPs, we're just now dealing with them individually. Instead of adding another field to the group, it made more sense, we thought, to move forward with a flattened structure so we can be more flexible in the future if we need to make more changes. This was kind of a big change. We had new endpoints for the flattened LRPs and new events and new event endpoints as well. And we internally also stopped using groups and that sort of logic in our internal implementation. So each long-running process now has a presence field. Ordinary means that the LRP is running normally. It's kind of a combination of the cell state and the LRP state together. Evacuating is an LRP that's on a cell that's evacuating, and suspect is on a cell that's, we don't know what's actually happening with it. It hasn't checked in with locket, so it might be gone, it might not be. So with this change, what happens now? LRPs on the missing cell aren't immediately replaced. They're marked as suspect. And replacements are created, but they're not immediately used. They're kind of waiting until we know that we should use them. Since we don't technically know the state of the cell, we're kind of optimistic and expecting work to continue running to ensure that the maximal routability to your app happens. So during like small environmental flakes, like one missed check-in with locket, if Convergence notices that, we don't want to drop routing to your applications. We want to maintain altitude as much as possible. So if a cell goes missing, the replacements, once they start running, then they take over. They take over the routes to that application, and the original replacements are deleted. So you should have a seamless transition if a cell kind of blips out of presence. If a cell is unable to talk with locket, then you should have a seamless transition and not have any downtime for your applications running on that cell. So yeah, so here we're just seeing the removal of the LRPs from the database. They're no longer going to be routable. However, if the cell actually ends up coming back, so the next time it's able to check in with the locket and the control plane is able to find it again, we just delete the replacements. We know that the original instances are already running. They're already in a good state. We don't need to penalize the cell for missing a heartbeat. We just keep those running and use them and get rid of the old instances. So this behavior is now default in Diego as of version 2.27 and is something that you should be expecting to see in your environments if you're on the latest stuff. You should not see any downtime when you have sort of these little environmental flakes in your environment, and should have a higher availability for your applications.
Next up, we have savings. We want to prioritize the highest value work for our users and Diego team, so we spend our time and money more efficiently. With the ability of having multiple runtimes in the future, we want to focus on the right things within our team so that we can realize the goals of the community and the foundation. And that means prioritizing and deprioritizing work that ensure future savings and effort for the core CF teams. This means that refining and fixing the current feature set that are in the Diego is a high priority for us, and introducing new features is not as high a priority. If a feature set can be realized as part of the evolution of the platform, it might be best to start it there. Another area that we are continuing to focus on is the continued focus on the Diego operator experience, reducing the time to debug components and app failures. That's an area that we have heard from users and customers that they would like to have more visibility into and have an easier time debugging these failures when and if that happens.
And of course, the last S, security. We expect Diego components to be secured by default, and the vulnerabilities are patched in a timely manner. So part of getting TLS and having all communication paths secured over TLS, we secured some more endpoints and more services that we talk to. When you're doing a CFSSH, so for operators that are concerned about ports on their Diego cells that are open that are not TLS endpoints, you can actually now disable those endpoints if you are not using TCP routing, and your app traffic and CFSSH traffic will go over TLS ports that are proxied by the Envoy proxy that comes with each of your application instances, and everything will be over TLS in that regard. It's not currently compatible with TCP routing, but if you just have HTTP apps, everything should be fine. And of course, also, we're trying to work on updating dependencies in a more automated fashion, continuing to, with that automation, Envoy proxy that we use, put with each one of your applications, automatically updating that, Golang, and any of the libraries that we depend on in our code base.
That's all we have for you. Shout outs that we want to give out to our PM, Josh here, other developers on the team, Maria and Nick, the CF Components team that we work closely with, Build Packs, Cappy, CF Networking, Garden Windows, and Percy. More importantly, the CF community, every one of you. There's a lot of these issues have been discovered via GitHub issues and Slack, so please keep them coming. This is how we can make the system more robust and more stable. And if you're experiencing any issues at scale, as far as the scheduling, as far as your app crashes, please let us know. If you'd like to have a better experience debugging these failures, please let us know. With that, we have a few minutes for any questions if you have.
Doesn't have to only be about what's in the talk. Any other Diego questions if you have them, but sounds like no.
Awesome.
All right.
Thank you all.
Thank you guys.